Hi, I'm the Exceleer. In this video I'll show you my take on how to calculate the distinct count of visible cells only, and this in a purely Excel Classic environment, meaning no use of any of the power tools like Power Query, etc., just the classic Excel grid that we all know and love. I will also show you some related formulas because they will help with the explanation. Now, as a general rule in my videos, I want to explain things intuitively and also be efficient and effective. Therefore, I will not verbalize every single key press I use, let alone repeat that every single time. I prefer to be a little less tedious, be efficient, and focus on the main topic. Alright, let's dive right in. Here we have a small fact table. It consists of several text columns and also a number column named score. We want to make sure that our formula for distinct count of visible cells only works for both text and number columns, therefore I will work via the intermediacy of an input column, like so. It's of no consequence for the formula, it just enables me to switch quickly between columns without having to change the formula itself. So let's see, we'll start with a text column, make it first name, the column gets copied into input, and the selected column is highlighted in the table. Next, let's get to know these columns a little better. The column of last names consists of unique values, all distinct. The first name and score columns, not so much. We'll use them in our formula. To prove what I just said, let's look at the following formula. Distinct count all cells. It's a very simple formula. Take a column, wrap it in unique, wrap that in count A, and done. What does it give us? A distinct count, yes, but of all cells, regardless of their visibility. It's in the neighborhood, but not exactly the formula we're looking for. Another formula is this one. Count rows, visible cells only. It's an even easier formula. Just the subtotal number 103 of the input and done. This function takes into account the aspect of visibility, but it cannot do a distinct count. Again, it's in the neighborhood, but not exactly the formula we're looking for. Now mind you, I'm not showing you these formulas for nothing. We need certain characteristics from both of them, you'll see. The last column in the fact table, the country column, is more of a category column and we'll use it to filter the table. For that purpose, I'll display a slicer. And I'll filter for Germany and Mexico. As you can see, all formulas behave as their labels suggest. Now it's time to look at the formula for the distinct count of visible cells only. This one is not so simple, so I'll break it down in discrete steps. For this I use the let function. The let function allows us to define local variables that exist only on the inside of that let function. I prefer to call these local variables steps, because that makes for a more intuitive way to explain the sequence of events. Every step has a name and a formula separated by a comma. The results of any previous steps can be used in subsequent steps simply by referring to their names. This makes for simple and efficient formulas. As the last argument in the let function, we can put the name of any step, and by doing so, the output of that step becomes the output of the let function as a whole. Now let's go over all the steps in sequence, starting from the top. The first step I always like to call the source step, and in this case it's very simple. Just get the input column. I'll visualize the results of the steps right here below the slicer. So this is the contents of the source step. Now mind you, as you can see, regardless of the filtering in the table, the source step will always contain the complete input vector, not the filtered one. By the way, I use the term vector in the numerical sense, not in the mathematical tensor sense. Just think of terms like vector computer, vector processor, vectorization. It corresponds to an array of values as opposed to a single scalar value. So again, the source step contains the complete input vector. Next, for this source step, we compute an index from 0. And it's exactly what the name says. How do we do that? Well, we calculate a linear sequence as long as the length of the source step starting from 0. And of course, it looks like this. Next, the third step. Well, the third step is the pièce de résistance of this 5-course meal. I call it is visible, and it's the most intricate step of the entire formula. What we want is a flag that indicates whether or not a record is visible, and this for every record in the source vector. That exact result is obtained by this intricate formula. Here's the result. Let's analyze this. First off, let me remind you what a column vector looks like in line in the formula bar. Let's look at inputs. Curly brackets and text values separated by semicolons, a typical column vector. Next, we look at the result of what the offset function gives us. What do you know? It looks exactly the same in every way. Now, don't be misguided. You might be tempted to substitute this offset function construct for just the input vector, but we actually already know that won't work, because that formula yields a completely different result. And here it is. Subtotal 103 of input, it gives us a count rows of visible cells only, not exactly what we want. So using this perhaps a little convoluted offset construct is actually a requirement. Okay, let's look closer at our third step and work from the inside out. We use the offset function, which takes 5 arguments. For the first argument, the starting position, we use source. We might as well have put in just the first element of the source vector. We'd get exactly the same result, but putting in the name of the whole vector makes for a more elegant solution. For the second argument, the vertical offset, we use index from 0. Now, by default, this argument is expected to be scalar valued, but we put in a whole vector, so we effectively vectorized the offset function in that second argument. Therefore, the result of offset will also be a vector of the same dimensions as index from 0. For the third argument, the horizontal offset, we use 0, no offset. For the fourth argument, the vertical length of the array offset will extract, we must put in 1, explicitly. This cannot be omitted because of the vectorization in the second argument. Only this way we ensure that the records are extracted one at a time, and the iteration and thus vectorization over index from 0 occurs as required. The fifth and final argument has a default of 1 and can be left out. As a result, the offset function iterates over the entire source vector, extracts one record at a time, and presents those records to the subtotal 103 function. Now, 103 means count A, but visible cells only, which, of course, is exactly what we want. So, as a result, visible cells get a 1 and hidden cells get a 0. Hence, the isVisible vector of 1s and 0s. And of course, in line, it looks just like this. Curly brackets, numbers separated by semicolons, this exact column vector. Now, let's contemplate the consequences of this isVisible step for just one moment. In DAX terms, we have a scalar valued measure, a function, that now is fully aware of the external filter context applied to a fact table. And we can modify that external filter context at will at any time we want. So external filter context aware measures in Excel Classic, no problem. And that is no small feat, and all in all not so difficult to compute. Let that sink in for a moment. Okay, moving on. Now that we have that isVisible vector, we can use it as a filter mask on the source vector. And that's exactly what we do in the next step, visible source data. The formula is simple. If is visible, then source, else empty string. And this is the result. Now that we have reduced the source vector to just the visible source data, the only thing we need to do is to calculate a distinct count of the letter vector. And we all know exactly how to do that, right? Wrap it in unique, then wrap it in count A, and we're done, right? Well, almost. You see, by reducing the source vector to just the visible source data, we've introduced an empty string. Let me show you. There it is. And that by itself will be counted by the countA function, so we need to compensate for that, hence the -1 here. Except in the case where all the records are visible, then we do not introduce the empty string, and we should not compensate for it. In that case, when all rows are visible, all records in the isVisible column are equal to 1. And thus the product of all these records will be equal to 1 as well. And thus, in that case, in this way, by subtracting the product of isVisible, we neutralize the -1. Just a small trick. And of course, here we have the result. A distinct count of 4 and done. Oh, there's just one more thing. And what about number columns? Well, let's change the input column to score. Equals score, everything updates, and oh yeah, 14 appears twice, so we have a distinct count of 6. There you see, the formula works for both text and number columns. There you have it. Alright, hope you liked the video, and I'll see you in the next one.